Welcome back to the classroom. My name is Mr. Wong, and today we'll be looking at advanced mechanics, which is Module 5 of HSE Physics. And we are going to look at inquiry question 3, motion in gravitational fields. This is the dot point we'll be covering. The title of our lesson will be the total energy of satellites. And what we're looking at is deriving the relationship between gravitational, potential, and kinetic energy, along with total energy of satellites and planets in their particular orbits. We're going to try and apply quantitatively the relationship. So we're trying to do some calculations to demonstrate how gravitational force and energy will affect these types of situations. So let's begin. Okay, before we talk about gravitational potential in space, let's firstly talk about gravitational potential on Earth. So the way we measure it, we always say that gravitational potential is due to a positional change of the object, where gravity can apply work on it to make it move. So if I move this block here and take it to point X, gravity has the capacity to accelerate the block from point X back down here. So at this point here, there's a certain amount of gravitational potential. Okay. We firstly defined gravitational potential as work being done by gravity. So if we have force times displacement, the force that we're applying is the gravitational or the weight force times the displacement, in this case, the height of the object. And so we get this formula here. But there's one specific issue, that is g here is not a constant value in space. Okay, on Earth, on average, the acceleration due to gravity is relatively similar, no matter where you are, but not in space. We also know that this concept of h, so I'll write that down as well. We take h as the 0 point of where we are measuring. You could sort of think of it as this is the point at which there is no gravitational potential energy. However, we know that Earth is not at the center of the universe, so it cannot be the thing that attracts everything together. So we can't technically have zero gravitational potential energy on the surface of Earth. We have to change our perspective when we're in space. And as we talked about, g is not constant. If you actually have a look, this is a nice little graph that illustrates the changes in gravitational acceleration as we move further and further away from Earth. You can see it is sort of like an exponential decay. So if this is continuously changing, that means that this g here isn't a correct illustration of the object's gravitational potential, because when we use this value here, we are assuming that g is constant. And as we said, h, what we call the zero ground state, that is also not going to be the case because Earth is not the 0 point in space. So we need to find a new 0 point. We already showed how to find acceleration due to gravity based on the different distances from the Earth's center using this formula here, which was derived from this formula here, Newton's law of universal gravitation. Okay, so let's just quickly summarize what the issue of the old formula, why the old formula is not sufficient, mgh. Earth is not in the ground state, or it's not our zero reference point. So as a consequence, we need to find a new 0 point. Point number 2 is gravitational field strength is not constant as the distance from the Earth's surface increases, as we can see from this formula here. So let's try and work out where that 0 point potentially could be, and then go from there. Okay, so this is where we need to look into Newton's law of universal gravitation, right? So force equals to big G, big M times M over R squared. Now, if we use this simply in terms of the mathematics, when the radius of separation between the two objects is incredibly far, so towards infinity, so the larger R gets, the closer F approaches to 0. Okay, so what we could say is potentially at a distance of infinity, which is, let's just say this random point here, the gravitational force is 0. Now, as a consequence, what that actually means is our work being done by gravity is also 0 here. Okay, so if gravity can't do any work at infinity point here, that probably suggests that gravitational potential energy, GPE, is 0 at when R is infinity. Obviously, the question lies is this is there a technical point like this? Probably no, in terms of a technical point like that, but the mathematics helps us with this calculation here. And so we make the assumption that gravitational potential is 0 at infinity point here. Okay, so there's that. Now the next point is if we drag this object from 0 all the way over to here, what type of work are we doing? Is it work being done by gravity or work being, or what, I should say that again, is it work being done against gravity or is it work being done with gravity? Now, originally we said that if we're on Earth and we move an object from the surface to Earth up, okay, we will see that there is a change. So we're doing work against gravity. We also said if we're going down like so, work being done with gravity, we're losing potential energy, right? So we're seeing a change, negative change in potential energy, and that's becoming work done. Same idea over here, which is kind of strange because we start at 0 here, whilst if we start from Earth, it's a positive value. But what we can actually tell is if we move an object from this infinity point towards here, right, we're actually seeing a decrease in the gravitational potential. So again, gravitational potential energy will actually be decreasing as we use work with gravity to pull this object towards a specific position that we want to see. Okay, so work must be done to move against gravity from here to here. That's positive work being done. When we're moving an object with gravity, we're doing negative work. We get negative GPE. Okay, so what we can actually say is if we want to derive a value for gravitational potential, it's actually a negative value we'll get overall because it's negative work being done. Or so to speak, it's work being done with gravity. So this is our old formula. We know what the variations of G is. That's given by our formula here. So we're going to substitute G into our original formula, and we get this new little depiction here. mgm divided by r squared times r. Okay, now we also know that there is a reference point change. Okay, so firstly, just cancel everything out here. So we get this equation here. But we know that due to the change in the reference point, where infinity is equal to 0, the formula becomes a negative value. So a negative value here. And that's because work is being done with gravity, not against gravity this time. To move the object into its position. Okay, so that's what you have there. Now, if you're not totally convinced by this, when Einstein actually came up with, or when you actually come up with the equation for gravitational potential, you actually use, I think it was either differentiation or integration from the universal gravitational law of force to find this, and that explains the negative as well. So this is sort of a sort of a simplistic view of why it's a negative value. But if you were to actually do the proper mathematical uh, integrations and differentiations, you'll come to the same conclusion as well. Okay, so that gives us a nice little explanation of gravitational potential. It is the amount of energy an object has due to its position within the gravitational field. If you actually have a look at our diagram here, we start at 0 where r is very far, and we gradually get more and more negative, or we get an increasing negative trend down here. Okay, and we get to this point here. Okay, so as an object approaches closer and closer to another big mass object like Earth, their gravitational potential will decrease further and further towards the negative. Okay, so that's what we have. All right, we do have some questions that we can go through in this recording, but we'll save that for another recording following through, because I want to go through all the theory in this one, and then we'll go back to the questions. Okay, so we go back to planetary motion. Of course, the assumption we're making here is when a satellite or planet is orbiting around a larger object, we have a complete uniform circular motion. That's not necessarily the case, but for our little investigation, this is very sufficient information. So, if a satellite is performing uniform circular motion, that means its centripetal force is generated by the gravitational force of the larger object they're orbiting. So again, we come back to this equation here. All right. Now, before we when we looked at this equation, we actually demonstrated how it can relate with Kepler's law of planetary motion. We also use this to find orbital velocity. But what I want to show you here is what if I just got rid of the r's on both sides, and I got this formula here. So I've cancelled out this r here, I've cancelled the r squared here to just r, and you get this formula here. Now, if we have a look at this formula component here is essentially gravitational potential energy, obviously minusing the negative component, right? So that's kind of gravitational potential. Now on this side of the equation, you get this equation here. Now, if we actually have a look at this equation here, it's actually quite similar to kinetic energy. Kinetic energy is half mv squared. Now, what you have here is twice the amount of kinetic energy, so 2k. Okay, so if I was to substitute kinetic energy into here, so I get 2k equals to big G m over r, and I divide both sides by 2, this is the equation for kinetic energy of a planet or satellite orbiting around another object. Okay, so that's what we have here. What you can also see and appreciate is that gravitational potential is twice the amount of kinetic energy, and it's also a different sign. So gravitational potential, we can almost say kinetic energy, okay, or gravitational potential is twice the amount of kinetic energy, and it's also on a different signage. Kinetic energy is positive, gravitational potential energy is negative. So that's how you can demonstrate using the formulas here. Be very careful with your derivations and also be very comfortable with how to derive this using these kind of principles we're talking about. Think of everything as a holistic view when we do this. Now, let's have a look at the total energy. Okay, so you might have already had a look beforehand. We might go back to this a little bit later. Let's just firstly look at the total energy or mechanical energy of a satellite or planet in motion. Okay, so we already know the equation. Total energy equals to potential plus kinetic. In this case, because we're looking at a satellite, it's going to be gravitational potential. Now we already know what the formula for gravitational potential is. It's negative gmm over r plus kinetic energy, which is gmm over 2r. Okay, now simply put, if we were to get rid of all these values, because these would be constants when we're doing our, you know, addition and calculation, the equation looks more like this. So negative 1, so to speak, because the r would be constant, plus 1 over 2, a half. Okay, so by that count, our total energy of our satellite would be negative a half, and that's represented by our formula here. So I'll just get rid of those ink marks. So this formula here, negative gmm divided by 2r, is the total energy that a satellite would have in its circular orbit. And we have another nice little way of expressing this. We can say that the energy total is equal to half the amount of the gravitational potential, but it is the same value as the satellite's kinetic energy, except it's a negative value of it. Okay, or they are opposite values to each other. We can actually see this by our little diagram here. So it's a nice little simulation that I might just show on a separate video. But as this satellite is orbiting around our planet, imagining it's a circular shape, so that's not perfectly circular, looks more like an egg, but imagine it's perfectly circular. This value you have up here, that's the kinetic energy of our planet, right? This value we have here is the gravitational potential energy. This value we have here is the energy total. If you have a look at what we said before, that the energy total is equal to the half of the gravitational potential, that's correct, because this is about, what is this mark? Let's say it's like 2.3, 2.5, and then this is 5 down here, negative 5 down here, and then we have a negative, or we have positive 2.5 up here, because kinetic energy is equal to the amount of total energy we have, but it's in the opposite signage. So that's consistent with the formula we just derived here. Okay, so these are the formulas that we looked into. We said that kinetic energy is demonstrated by this formula here. Now, this one isn't given to you on your data sheet. So you will need to remember it off by heart, or at the very least be comfortable enough to derive it by yourself. essentially. Let's have a look. Gravitational potential energy is on your data sheet. However, total energy is not on your data sheet. It's on your syllabus. So it's given to you on your syllabus, but it's not on your data sheet either. So you will also need to remember how to derive this, or at the very least what the formula for it is. And obviously this relationship between total energy, gravitational potential energy, and kinetic energy is obviously not on the data sheet either. So you will also need to remember this relationship, or at the very least know how to derive it. All right, so that concludes the theory component of this lesson about total energy of planets and satellites in orbit. We talked about gravitational potential, why it's a negative value. We talked about how to derive kinetic energy. We talked about how to derive the total energy. Okay, our next lesson will look into escape velocity and orbital velocity again. But if you found this video useful, hit the like and subscribe button. And also, don't forget to join me when we do the calculation questions for this particular lesson. I'll see you next time.